SwayamPrabha. Digital India. Educated India.
Good morning everybody. In the domain of materials, so far we have covered metals and ceramics. So now we will go to a new domain of materials, which is the polymers. So we will first start with a basic introduction to the polymers, and then we will gradually see what are the very specific mechanical properties of polymers and what is the mechanical behavior, what is so interesting about the behavior of polymeric materials. But as an introduction today, we will first have a discussion on the basics of polymers, and then we will also try to characterize the polymers based on different types of classification criteria, and some applications we will keep in our mind. So this will just give us kind of overview of the world of polymers. Now the word polymer has that Greek part in it, where the poly means many and mar means part. So that means whatever polymers you see, it is essentially made of many individual parts. Each one of these individual part is actually called a monomer, a single part. Now once I consider two monomers together, if they join their hands, then they become a dimer. So a monomer also by definition, it has a degree of polymerization or dP, which is 1. Now if there are two monomers, then the degree of polymerization becomes 2. So for dimer it will be degree of polymerization which is 2. If you add a monomer with a dimer, you will get a trimer, and the degree of polymerization will become 3. Of course, this one unit adding together, or such kind of very small number of units happen for materials like silicon, in which there is a term called oligomer. So that means there are something like 5, 6 or 10 of the monomers join their hands together. But for carbon, on which our life the entire life in earth has developed, it does not bind only 10 numbers or 15 numbers or 100 numbers, but of millions of such carbon molecules can easily get bonded with each other. So specifically keeping carbon in mind in the polymer, our definition is something like a n number of degree of polymerization, or n mar with a m mar. Two such polymers, when they add together, concatenate, then you get something like a n plus m mar with a degree of polymerization of n plus m. So that is the kind of a very big scale polymer that we are talking about. Now how do we classify the polymers? There are various ways in which we can classify the polymers. We will discuss them one by one today. For example, you can classify the polymers on the basis of their molecular structure. If you try to do that, I will show you that it starts with the simplest molecular structure where it is completely linear, then it can be branched, that means some branching coming out of the linear, then it can be cross linked, that means the branches are chemically linked, and then it can be network. So that is the molecular structure wise. If you look at it from the origin point of view, you can very simply divide polymers into two types. One is the which is having natural origin, so natural polymers, and synthetic polymers. So that is this group. And then from the polymerization reaction point of view, that means how the polymer is developed, if you look at it, then two most important types are chain polymerization and step polymerization. So that is from the polymerization reaction point of view. Then from the thermophysical behavior point of view, we generally classify the polymers into two groups. One is the tacky so called polymers, which can actually you can give it many kind of forms. So that is thermoplastics, and the other group which with respect to temperature you can give it a set form, that is the thermosets. So, that is another way of classifying the polymers. Then in terms of the applications, there are end use of applications of polymers, that is also another way of looking at polymers, and there are some polymers which are actually advanced polymers. So, these advanced polymers, okay, so that is like UHMWP or liquid crystal polymers, that is like some of the advanced versions of the polymers. So, let us try to look at them one by one. Now, from the the origin point of view, if you look at the polymers, then you can, I told you that you can divide into two groups, natural polymers and synthetic polymers. Natural polymers are like the shellacs or bioadhesives, okay. Say for example, you can consider some of the latex of the tree that comes out, or the cotton or the silk, okay, natural rubber, okay, shellacs of course I told you, and then the starch which you get from potato, okay, or the cellulose that you get from some of the plants. These are all some of the examples of our bone itself, some of the examples of natural polymer, and some of the examples of synthetic polymer. Our world today is actually surrounded by all sorts of synthetic polymers like synthetic rubber, bakelite, neoprene, which is also a form of rubber, nylon for example, polystyrene, polyethylene, PVCs. So, there are so many of them, the synthetic polymers. Okay. So, that is as far as the origin of the polymer goes. Now, if you try to divide it in a different way, more like a fundamental point of view, then you can actually characterize polymers in terms of their molecular structure. So, that is something that is little more advanced than in terms of, instead of dividing them in terms of the origin of the polymers. So, here what you will see is that the polymers are essentially of three types, that is the linear polymers, then the branched polymers, and then those which are chemically linked. In fact, out of them there are two types we call it. One is actually then when there is a cross-linked structure, and another is when there is a network structure. So, to begin with, we will first see the linear structure polymers. So, some polymer units are just like monomers joining their hands together and building up the longish chains, okay. Something like polyethylene. Polyethylenes are single units of ethylenes, you just add them all together, you get a long chain polyethylene. These are the each one of them of course along their axis, because of covalent bonding they are very very strong, okay. But if you think of the transverse direction between the two, then there is not much of a a bonding force there. This will be either very weak van der Waals bonding or hydrogen bonding kind of things. So, as a result, they have first of all directionality. In one direction they will be exceptionally strong and high modulus of elasticity. On the other hand, in another direction they would not be, so they will be weaker, and they are soluble, they are fusible because of this kind of structures, and they are green also. You can use them many a times. That is why polyethylene, the films, you can actually reuse them or recycle them very easily. So, the examples are like high density polyethylene, low density polyethylenes, etc., and then PVCs, polystyrene, nylon, PMMA, all of them are good examples of the linear structure. The other point is that linear structure also generally they have actually good what you call the crystal structure, okay. So, because their repeativity is generally very good, and as a result many of the linear structures, not all but many of them, are actually highly crystalline. So, the degree of crystallinity, if it increases, that also improves the mechanical property of the system. Now, some of them, the linear structures are not just linear, but they are branched type of structures. So, that means there are side branches or chains that are connected to the main ones chemically, okay. But with the another such link, there may be only once again hydrogen bond or van der Waals bonds, etc. So, they are more soluble and feasible, and this is like low density polyethylene is one of them. So, that is linear, but there are some branches with them. Now, if the branches kind of gets cross linked, so that is what is the cross link structure, then what you are getting is that the adjacent linear chains are joined one to another at various positions by actually covalent bonds, and they become insoluble and infusible. So, that is what is the cross link structure. If this degree of cross linking increases so much that they form a network structure with high cross linking and 3D network, then that is the extreme form of cross linking, and this will become insoluble and infusible like rubber, polyurethane, phenol formaldehyde, or what we normally call epoxy, epoxy resins. So, that is the ultimate example of network structure. So, this also is important in the sense that cross linked and network structures are actually mechanically more rigid than the linear and the branch structures, and there is a correlationship between this kind of the from the in terms of the growth of the polymer from the molecular structure point of view and the thermophysical point of view, how we categorize it, there is a correlationship between them, and that is, if you see the polymer is if you find it to be linear or branched, then there is a high degree of probability that it is a thermoplastic polymer. On the other hand, if it is cross linked or if it is networked, then it is more possible that it is a thermoset polymer. Now, thermoplastic polymers, because of their nature that they are linear or at most branched, they are heat sensitive, they soften and they actually flow upon heating. It is very easily one chain can smooth over the other, and I told you that they are soluble and fusible, and this under many cycles of heating and cooling, thus they are recyclable. So, thermoplastic polymers are greener in comparison to thermoset polymers. Most linear polymers and those having some branch structure, I told you already that these are actually thermoplastics. Now, individual polymer molecules are held together by weak secondary forces like van der Waals force, hydrogen bonds, dipole-dipole interactions. These are the general type of weak bonds between the two chains. So, I have one chain and I have another one. Between them, the force that actually works between them is either van der Waals force or hydrogen bond or dipole-dipole interaction, and these are all weak bonds. These are all weak bonds, and that is why they are mechanically also they are weaker, particularly in the transverse direction. Easy to repair by welding, solvent bonding, etc. if there is a crack, because they are formable. So, you can actually apply a little bit of heat and then you can repair it. And also very interestingly, they have unlimited shelf life. This is commercially important. Suppose today I buy some monomer, and then later on I think of polymerizing it. Now, for these monomers to polymerize and form a thermoplastic polymer is something in which at least it will not get set, it will not be completely useless if the polymerization suddenly starts. But you imagine that you have purchased that super glue from the market and you just forgot switch to close the tip of it. What will happen? That there will be a polymerization reaction instantly as it comes out and get in contact of the air with oxygen, the reaction starts. So, there will be, it will constantly get thermoformed. So, it will become a thermoset, and as a result that particular glue will be useless very soon. So, then it has a very limited shelf life for the thermoset polymers, but thermoplastics do not suffer from this kind of problems. That is why it is almost like unlimited shelf life it is having. What is the disadvantage? It is prone to creep. Now, that you can easily see that since the chains can actually slip over each other with a little bit of force, because the force that holds them together is a weak force like van der Waals force or hydrogen bonding. Hence, it a little bit of force you can easily move one over the other. So the examples are like polyethylene, polystyrene, okay, PET that you see many a times for using some of the bottles, etc., PVCs, nylon, polypropylene, PMMA. PMMA, one of the uses in your dentists, for example, if you go, they actually make the teeth, artificial teeth or such kind of thing using PMMAs. So it's also known as dentist's powder. So that is the thermoplastic polymers. Now let us look at the thermoset polymers. Okay, before we do that, what are the typical applications? Suppose nylon, you know about the nylon wares, okay, and you also know that the nylon wares creep, and the creeping happens because of the thermoplastic nature. Then PVCs, polystyrene, which is used where there are more complex shapes, for example. PMMA, also it is known as there is a common name of it. It's call it some people call it acrylics actually. Okay, so you can you will get it in the market as artificial glasses, for example. They are transparent. Then polypropylene, which is used in the chairs, for example, and then PET, which is used in the bottles. Now let us look at the thermosetting polymers. Thermosetting polymers are actually network polymers. They are creep resistant, they are less sensitive to temperature, quite naturally, because unlike the linear polymers, here you have cross bondings and you have chemical bondings. So that means the individual chains are not very free to move with respect to each other. As a result, they are creep resistant. As a result, they are less sensitive to temperature, and they attain permanent hardness due to cross linking. And once they attain that, once again I want you to recall the super glue example, that once it gets networked, then it do not soften and flow upon heating. That is the good part of it. But then that also means that it is non post formable. Okay, so that means obtained in soluble or fusible stage in early or intermediate stage, but once they get cured, they will be infusible and insoluble. So as a result, their shell life is actually very limited, but the good part is that they have excellent thermal and chemical stability once it is polymerized. The mechanical disadvantageous part is that they are brittle, they are non-recyclable. So that is the flip side of it, and the examples are like bakelite, epoxies, urethane. Urethane is like the foams that you use in your sofa, for example. So that these are polyurethanes, PU, call it PU foams. PU foam is a very common name, and that is used in your sofas, etc. So that is the thermosetting polymers. Now in terms of applications, you can try to visualize that it's used in the magazines, it's used in the bakelite, hair dryer, okay, also of course the glues of epoxy A's, epoxy B's. There are sometimes you will see in market that there are two glues and you need to mix them together to actually initiate the polymerization reaction, because they are so sensitive, the heat sensitiveness and the shelf life is so limited. So its special care is taken that they do not automatically get networked like the super glues. So you will get them in two parts like epoxy A and epoxy B. You mix them in a particular stoichiometric ratio, the polymerization starts, and you will get a good hard thermoset polymer, which is used in composites. Now thermosets, that means it has to undergo a particular process called curing in order to get set. So the process to these from a monomer stage, first you are starting the process. So in liquid stage itself the branching is occurring and then the gel is forming. So some are branched, some are already chemically linked, so there is a sol and a gel phase, and from there the amorphous glassy phase will start as you increase by the addition of heat and sometimes pressure. The gelation, the vitrification will start and you will get a fully cured thermoset. Okay. So over the time, as this gelation is happening, the viscosity of the system will continuously increase, and in between you will get that intermittent phase of gelation where you will get a gel phase and a sol phase, as I told you, and with respect to time the sol phase will gradually decrease and the gel phase will increase, so that basically you get all interlinked phases, and then the hardening or the vitrification is going to occur in the system. The machine in which we generally do it, I just want to mention it to you at this point, is called an autoclave machine. Okay, it is used, say for example, when we make the aircraft wings. Okay, so this is composite these days, and in that composite, that matrix is nothing but a thermoset polymer. So that thermoset polymer is to be cured. So what you do is that you actually make this whole thing out of a thermoset polymer and then put it under temperature and pressure, so that it gets cured, the vitrification occur, and you get that beautiful wing shape. Now what happens in this polymerization process? We have told many a times the polymerization process from monomer to polymers. Now there are two types of polymerization process. One is called a chain or addition polymerization. So in this process, the monomer units are attached one at a time in a chain like fashion to form a linear macromolecule. Okay, so there are only a few active sites in this case from where these polymerization will start, like this is one active site, and then one after the other the process of polymerization is happening. Only very few such active sites are there. In fact, this will come as a catalyst is getting broken, then the decompose, then the active initiator R star will come. This R star, the moment it is going to react with a monomer, you get the first active unit, that is the RM1 star. Then as the chain will propagate, this RM1 star with work with another monomer to get RM2 star. Then that process will continue, like one RMN minus 1 star will give you an RMN star. When that process will stop, when one of this RMN star is going to react with another of the RMM star, then there will be a RMM plus N R formation. So as both the sides are now of the polymer is having two R's, it will lose its cutting teeth. That means the chain polymerization will stop at that instant. So that is what is the addition or the chain polymerization. Much unlike that, there is another type of polymerization where you don't have to really depend on one or two sites, but you can have simultaneous process of polymerization in many places. So like everywhere this is happening, and this is like it can involve more than one monomer species, and the monomers will react with any nearby monomer. They will not wait for some other active area to come and make them ready for the reaction. It would not happen, they will readily react. So no special activation is needed to allow a monomer to react, and a small molecular weight byproduct such as water that will be eliminated. That is why sometimes this step polymerization is also called condensation polymerization. A typical reaction is like you have this OH element and then this thing HO here. So H plus OH react with each other and you get the new one, and similarly you get in another case this OH plus HO and you get a new one. Every time you are getting some water or condensation out of the system. So that is what is a step polymerization. So, and this you will find in polymers like phenol, formaldehyde, nylons, polycarbonates. Okay, these are all produced by the condensation polymerization. Now we talk about some of the advanced polymers. One of them is ultra high molecular weight polyethylene like UHMWP. This is becoming very important today because these are linear polyethylenes, but it has very high molecular weight. Okay, what is the significance of high molecular weight? That means you have each monomer itself is so long that actually it gives you a high melting point, high mechanical, it gives you a high modulus of elasticity, etc. So there are two trade names of it, one is Spectra, another is Dyneema, and both of them have extremely high impact resistance, high resistance to wear and abrasion, very low coefficient of friction. They are self lubricating and they have non-stick surface, very good chemical resistance to normally encountered solvents, excellent low temperature property, and outstanding sound damping and energy absorption characteristics. Only thing is that their mechanical properties diminish rapidly with increasing temperature, because they are the linear polymers. So they are susceptible to, as I told you, creep like problems, but at if the temperature change is not very high, then they have excellent properties. They are used in femoral implants, pipes, light gears in Legos, etc. That's what one of the examples of advanced polymers. The another example of an advanced polymer is the liquid crystal polymers. So some of these aromatic polyesters based on p-hydroxybenzoic acid and related polymers, they come into this category. Now, why they are liquid crystal, we call it, because in the liquid state generally any material is supposed to be in a very amorphous state, but these materials in a liquid crystalline state you will get them. That means they will be neither purely crystalline nor purely liquid, so you can consider it to be a new state of matter. They are capable of forming regions of highly ordered structure while in the liquid phase, but regularity lower than the completely solid crystal. They are extremely unreactive and inert and highly resistant to fire. So something like your LCDs, the liquid crystal displays on digital watches or flat panel computer monitors, televisions and other digital displays, they are actually made of these liquid crystal polymers. Now let us try to categorize the polymers on the basis of the end use of applications. Okay, let us see what are the end uses of a polymer. The first end use is in terms of the films. Polymeric films you will get in various sizes in the market, from 25 micron, we also call it in terms of microns, 25 micron to 125 micron meter thin films that are used for packaging food products, and their important properties, they are low density, high degree of flexibility, high tensile and tear strength, their resistance to moisture and other chemicals. That is why we generally wrap it up. So examples are polyethylene wrapper, polypropylene, cellophanes, etc. So that is one group of polymers where it is mostly used as films. Then the other group I told you about these foams, right, the sofas for example, which has the foams. So there you have the polyurethane foams. So foams are another very important categories of polymers. They contain relatively high volume percentage of small pores and trapped gas bubbles. They are commonly used as cushions in automobiles and furnitures, as well as in packaging, in thermal insulations. You get the polymeric foams. So that is another end use. So films and foams. What else you will see? You will see polymers in coatings. For example, in paints, varnish, enamel, lacquer and shellac, you will see them, and they are used to protect the surface, and so that to protect it from corrosion, and for electric insulations, to improve the appearance of an object you apply the polymeric colors. So that is for the coating. The very important use of polymers, suppose you consider a silk saree. So it has silk fiber in it, and the fiber is very important application of a polymer, because it it has a very high degree of actually modulus of elasticity. It is anisotropic, and you can use it for various applications, including making jet aircrafts, right. So they are usually long filaments having at least 100:1 length to diameter ratio, and you can subject it to mechanical deformations like stretching, twisting, shearing, abrasion. They are very good to absorb this. They are used in textile industry for fabric cloths, which can be either woven or it can be used to make composites. Our next example of polymers is the adhesives. They are used to join a large variety of materials like metals, ceramics, polymers, composites, etc. And the advantage is that they are lighter in weight, they have the ability to join dissimilar materials, they have better fatigue resistance, and they have lower manufacturing costs. But the limitation is many times in terms of high temperature or in terms of impact resistance. So these are some of the problems with the polymeric adhesives. There are natural adhesives like animal glues or resins or proteins, starch and resins, okay, resin here, and artificial adhesives like epoxy, polyurethane, cyanoacrylate or acrylic polymers. They are used in aerospace, automobiles and various types of stationaries, etc. So that is also becoming very popular, use of polymers as adhesives. Then there is a good group of polymers which we call them to be elastomers. Now what does that mean? It means that if you look at this particular diagram, it will be very clear to you that any brittle material will show a high modulus of elasticity, but they will fail at a very low strain level. Okay. Now the plastics, they will become non-elastic beyond a certain point, then the plastic strain will grow until it fails. The elastomers on the other hand, they actually remain elastic. That means if you actually unload it, it will trace the same path, but they can take a very large deformation. So they remain elastic even though in a non-linear manner, highly non-linear, but they can take up a very large strain. So naturally whenever we talk of elastomers, what comes in our mind are the rubbers, for example. So they have very weak intermolecular forces, low Young's modulus and high failure strain. That high failure strain is very important for them. So for a polymer to be an elastomer, it must not easily crystallize because the molecular chain should remain naturally coiled in the unstressed state. The chain bond rotations must be free to readily respond to an applied force. Delayed plastic deformation should be there. The examples are silicon rubber, butyl rubber, nitrile rubber, neoprenes, etc. There are applications like gasket seals, noise and vibration damper, car door seals, etc. So that is about the elastomers. The plastics, I already told you that this is like it is in between the elastomers and the brittle materials. They are malleable, can be molded into solid objects of diverse shapes. Some plastics are very rigid and brittle and others are flexible. They are used for all general purpose applications like some toys or very quick rapid prototypes you want to make, you use the plastics, and they can be either thermoplastic or thermosetting. That is about the plastics. So let us try to keep some names of thermoplastics for reference, like ABS, which is used in all the what you call rapid prototyping purposes. So this is used mostly for rapid prototyping. Then the acrylics, I told you the plexiglass is one of the examples. It is used in lenses, transparent aircraft enclosures, okay, outdoor signs, etc. Fluorocarbons like Teflon group, which is used in anti-corrosive seals, chemical pipes and valves, because it is very much it's a high temperature resistant anti-corrosive material. Polyamide like nylon group, used in bearings, gears, cams, brush handles, etc. Polypropylene, which is used in sterilized bottles, packaging films, cabinets, etc. Polystyrene, which is used in wall tiles, battery cases, toys, indoor lighting panels. they have a luster in them. Typical example is like Carinex, Dilene, etc. Polyester, like this, fibers, Dacrons, Mylar, they are used in recording tapes, clothing, automotive tire cords, beverage containers, and polyethylene, which is, it very well, that it is used in flexible bottles, toys, battery parts, tumblers, all sorts of very general purpose applications. Now there are the thermosettings, and there are three important thermosettings there. One is the amorphous one, that is the phenol formaldehyde. The trade name is bakelite. It is used in telephones, motor housings, etc. Then the epoxies, it is also amorphous. The popular trade name is araldite, which is used in adhesives, protective coatings, fiberglass laminates. And then the polyesters, it can be thermoplastic or thermosetting, which means it can be either amorphous or it can be semi-crystalline. There are many trade names like Laminac, Selectron, etc., which is used in helmets, fiberglass boards, etc., chairs. So these are thermosettings, some of the regular thermosettings for your reference. So this is what we have given a brief introduction to the world of polymers. In the next lecture, I will talk about how to calculate the molecular weight of a polymer. I will talk about the polymeric structure and the tacticity of a polymer. Thank you.